In 1656, Reverend John Wallis published a result with an impact so profound it would shape the future of calculus for the centuries to come. Today, we will embark on an epic journey in time to uncover the secrets of the Wallis integral. Let us draw a circle, and to facilitate our task, we will suppose it is a trigonometric circle of radius 1, which we can thus define by the following equation. Now the goal here is to calculate the shaded area. Using the standard area formula for circles, we know that it is equal to 1/4 times pi times 1 squared, so pi over 4. But from our first equation, we can also deduce that y equals the square root of 1 minus x squared. As such, the shaded area corresponds to the integral between 0 and 1 of the square root of 1 minus x squared. We thus have the following equation. This formula was discovered by Wallis in 1656, but in a completely different way. Indeed, in 1656, calculus had yet to be born, so such integrals could not have easily been studied. Instead, Wallis set off to find the curvature of curves whose ordinates were expressed by the following formula, with p and q being positive integers. By interpolating those different values, he arrived to the same equation and managed to find an expression yielding pi, known as the Wallis product. Wallis thus initiated the study of these family of integrals, which would later be known as the Wallis integrals. And yet those of you who have already encountered the Wallis integral somewhere else before might hardly recognize them. Indeed, the Wallis integrals are often expressed using the following formula. Now you might be wondering, how on earth is this connected to the integral we had before? Well, say we plugged in p equals 1/2 and q equals n minus 1/2 in this integral. Now let us carry out a u substitution by setting x equal to sine of t, which thus implies dx, equal cosine of t dt. If you're not very familiar with u substitution, I would highly recommend you to go check some videos explaining it in more detail and then come back. So this is where the magic of the Wallis integrals reveals itself. Notice how 1 minus sine squared of t equals cosine squared of t. When you expand this integral, you are left with the integral between 0 and 1 of the cosine function raised to the nth power. Now you can replace the cosine function by a sine function without changing the value of the integral, which you can verify using a simple u substitution. And there you have the famous formula found in every calculus textbook. If you wanted to go a bit further using an integration by parts, you can easily find the recurrence relation characterizing this integral. W of n plus 2 equals n plus 1 over n plus 2 times w of n, along with the two expressions of the Wallis integral for even and odd integers, which can once again easily be found using the previous formula. But this is not what we're going to focus on in this video. Today, I want to show you some even deeper and more intriguing secrets about the Wallis integrals. But before we move on, it seems crucial to do a quick reminder on two essential functions in calculus, the beta and the gamma function. Essentially, the beta function can be defined by the following integral, while the gamma function is usually defined by this integral. Interestingly, the beta function can also be defined in terms of the gamma function, using the following formula. Now that is already a lot of formulas which we will not go over in more depth, but before we go back to the main focus of our video, it is also important to remember that gamma of 1/2 is equal to the square root of pi. Okay, now that we have finished this short refresher, let us go back to our first integral. Hopefully by now you might have noticed some similarities to the beta function. And sure enough, the x to the 1 over pth power might motivate us to carry out a u substitution by setting x equal to u to the pth power, which thus implies dx equals p times u to the p minus 1th power du. We are thus left with the following integral, which we can thus rewrite in this form. Notice how this last integral is exactly equal to p times the beta function of p and q plus 1. And if you remember well, this allows us to rewrite the original Wallis integrals in this form. Isn't it amazing how we managed to express what at the beginning stemmed from the area of a circle to a complex yet elegant product involving the extension of the factorials to real numbers? But our work here is not yet finished. We still have to express w of n as a product of gamma functions. Now, if you remember well, w of n corresponds to the original Wallis integrals for p equals 1/2 and q equals n minus 1 divided by 2. Going back to our current equation, we can thus write that the Wallis integrals are equal to gamma of 1/2 times gamma of n plus 1 divided by 2 divided by 2 gamma of n over 2 plus 1. This formula, which might seem worlds apart from anything we could have thought by looking at the Wallis integrals, not only gives us a satisfying explanation for the two formulas I presented to you earlier, but it also further reinforces the link between the number pi and the Wallis integrals. Since you must not forget that gamma of 1/2 equals the square root of pi. At last, after a fascinating journey through time, we have managed to uncover the secrets of the Wallis integrals. Thanks for watching and have a great one.